So, picture this. You've just poured your first cup of coffee.
Yeah.
You sit down at your desk and you open up your security dashboard.
Oh, the calm before the storm.
Exactly. You are a junior cybersecurity engineering student, maybe, in your very first real-world internship, and you are staring at a mountain. I mean, a literal mountain of software bugs, vulnerabilities, and potential exploits just flashing across your screen.
And every single one of them has that little red icon next to it, just screaming for attention.
Yeah, it's completely overwhelming. Like, you're looking at hundreds of security alerts staring back at you. And the million-dollar question for any junior engineer in this position is, well, how do you decide what to fix first?
Right.
Do you patch the server glitch? Do you fix the login portal? You literally can't do it all at once. And choosing wrong could leave a massive hole in your company's defenses.
Yeah, you need a system to filter out all that noise. You have to be able to mathematically, or, well, at least methodically, figure out which threat actually poses the greatest risk.
Which is exactly why we're here. So to help you figure out what to fix first, we are doing a deep dive into this stack of security framework documentation, white papers on the classic Microsoft Dread model, and the official CVSS and CWSS scoring guides that you send over.
Glad you got those. They're dense, but so important.
Very dense. But our mission today is to unpack this whole concept of threat ranking. The process of measuring the negative consequences of a threat so you can prioritize your risk mitigation strategy.
Exactly.
We're going to focus really heavily on the Dread model, explore its fatal flaw of subjectivity, which causes engineering teams to basically pull their hair out and then look at how the industry evolved to use, more objective alternatives.
Yeah, because understanding where these concepts came from it's honestly like learning Latin to understand English.
Oh, like that.
Right, like the historical frameworks, they really inform the DNA of the modern tools you're going to be using every single day. And historically, the industry standard was the Dread model.
Which was developed by Microsoft, right?
Yeah, by Microsoft's Security Development Lifecycle team, or their SDL team. It acts as a model to quantify and prioritize threats based on 5 specific criteria. And for each criterion, an analyst assigns a score from 0 to 10. Then those scores are, summed up or averaged to produce a final risk rating.
So DREAD is an acronym. And reading through the white papers, I saw the first D's stands for damage potential.
Correct.
Which, that makes intuitive sense. You want to know if a bug is going to leak a single, meaningless email?
Yeah.
Or burn down the entire database. So a 0 is no damage. A 5 might be a minor information leak. And a 10 is just a total nightmare scenario.
Total system destruction, complete data loss, yeah.
Right. But looking at the 0 to 10 scale for the other letters, how does that interact with the R, which stands for reproducibility?
So reproducibility asks how easy it is for an attacker to consistently force the attack to happen. It's essentially measuring the environmental conditions of the system.
Okay.
So a 0 means the attack only works under incredibly rare, like almost impossible conditions.
Like what?
Think of an extreme race condition where an attacker has to hit the server at the exact precise millisecond a background cleanup job is running.
Oh, wow. So an attacker would essentially have to win the lottery.
Pretty much, yeah.
Yeah.
And moving up that scale, a 5 means the attack is complex, but, doable. Maybe it requires very specific network timing or this elaborate social engineering payload.
Right, right.
But a 10 means the vulnerability is painfully easy to reproduce. The attack can be fully automated in a Python script, and it just works every single time without fail.
Okay, here is where the framework gets a little tricky for me, because the E stands for exploitability. But isn't exploitability basically just reproducibility again? Like, if something is easy to reproduce, isn't it highly exploitable?
I get why you'd think that, but they are closely related while measuring entirely different angles.
Okay, how so?
Reproducibility, like we just covered, is about the physics of the target system, right? Exploitability is about the work and the skill required by the human attacker.
Oh, I see.
Yeah, like how much effort and expertise does it take to actually launch this weapon?
Ah, okay. So one is about the system's defenses, and the other is about the attacker's resume.
That is a brilliant way to put it, actually, yeah. In the Dread model, a low exploitability score, say a 2.5, means the attacker needs really advanced programming skills, deep networking knowledge, and the ability to reverse engineer custom protocols.
So we're talking about highly trained nation-state level hackers.
Yeah, exactly. Now, what do you think a 10 is?
That absolutely anyone can do it.
Spot on. A 10 means a bored teenager with a standard web browser could trigger the exploit. No special software, no coding knowledge required.
Wow, okay. That is a massive distinction.
Yeah.
So that brings us to the A,
Yeah.
which is affected users. And this one feels pretty straightforward to me. It quantifies the user base impacted by the vulnerability, right?
Yep. That's it.
So 0 means no users,
Okay.
a 2.5 means a few isolated individuals, and I assume a 10 means absolutely everybody using the application is compromised.
A 10 does mean all users, yeah. But the really interesting nuance here happens right in the middle of the scale.
What do you mean?
Let's say a vulnerability only affects 5 people out of 1 million users.
Yeah.
You might instinctively score that a 1 or a 2, right?
Yeah, because 5 people is nothing.
Right. But what if those 5 people are the root system administrators?
Oh.
Yeah. The DREAD model tells us we have to push that score all the way up to an 8. The privilege level of the affected users carries massive weight.
Because compromising one admin is far more lethal than compromising 10,000 regular users.
Exactly.
Okay, so that leaves the final D, discoverability.
So discoverability measures how easy it is for an attacker or, even a security or researcher to find the threat in the first place. A 0 means the vulnerability is incredibly obscure.
Like, how obscure?
Like an attacker would need intimate access to your proprietary source code or your internal architectural diagrams just to even realize the flaw exists.
Like something buried super deep in a legacy backend system.
Right, exactly. A 5 means the flaw could be discovered by, say, analyzing server error logs or intercepting regular web traffic. But a 10 means it is painfully obvious to anyone looking.
Like what, an error message or something?
Yeah, the error might literally display the database credentials right there in the URL address bar, or just spew raw SQL code onto the public logging page.
Visualizing this entire DREAD formula, it strongly reminds me of rating a spicy food challenge at a restaurant.
Okay, I have to hear this breakdown. Go for it.
So if you're ranking how dangerous a hot pepper challenge is for the dining room, you can't just look at the pepper itself. First, you have to consider how hot the pepper actually is. That's the damage potential.
Okay, tracking.
But you also have to consider how easy it is to accidentally bite into it. Like, is the chef hiding it inside a massive complex burrito, or is it sitting right on top of a plain cracker? That covers exploitability and discoverability.
Oh, that's good.
Right. And finally, you have to look at how many people in the restaurant are being forced to eat the dish. That's your affected users.
Yeah.
You can't just say, well, it's a really hot pepper, so the risk is a 10. You have to combine all those vectors to truly measure the threat to the restaurant.
That analogy perfectly captures how distinct vectors combine to form a single risk profile. You absolutely need context to understand the danger. Though reviewing the white papers you provided, it's interesting because many engineering teams began heavily modifying this model over time.
Really? How so?
They created a variant known as DREAD-D by just entirely dropping that final discoverability metric.
Wait, why drop discoverability? If a bug is impossible to find, shouldn't it be prioritized lower than a bug that's sitting right on the homepage?
Well, relying on security through obscurity is a very dangerous game.
Ah, I see.
Yeah, the industry basically shifted to the assumption that given enough time, every single flaw is eventually going to be discovered. I mean, automated scanners get better every single day, and malicious actors are just relentless. If you give a critical vulnerability a low overall score simply because you personally think it's well hidden, you are essentially leaving a ticking time bomb in your code. So by dropping discoverability, teams ensure that the severity is judged solely on impact and mechanics, not on the mere hope of staying hidden.
Okay, that makes total sense. So we have this robust framework. You score the damage, the reproducibility, the exploitability, the affected users. You crunch the numbers, you get a final score, and boom, you know exactly what to fix first.
In theory.
Right. It sounds like the ultimate tool for our junior engineers staring at their dashboard. Yet the documentation clearly states DREAD is largely retired as an official standard. So what went wrong?
The downfall of DREAD actually had nothing to do with the categories themselves. The categories are incredibly smart. The fatal flaw of the framework was its inherent subjectivity.
Wait, I have to push back on that. We just walked through a very strict 0 to 10 numerical scale. How can a math formula be subjective? Like if a vulnerability leaks user data, it gets an 8. A number is just a number.
That is the illusion of qualitative labels masquerading as quantitative data.
Okay.
The problem is human psychology. Let's run a quick simulation. Imagine a vulnerability causes an intermittent system crash on the internal employee chat server. Okay? It goes down for exactly 3 minutes once a day. How do you, personally, score the damage potential?
Well, it's not total destruction, which would be a 10.
Hmm.
but it's definitely interrupting operations. I'd probably score that a 6, maybe a 7.
Okay, now imagine the person sitting next to you is a seasoned senior developer who previously survived a massive company-ending ransomware attack.
Oh boy.
To them, a 3-minute chat server outage is a joke. They might score the damage potential a 2. On the flip side, a brand new junior developer might panic at the word crash and score it a 9. The white papers highlight that these qualitative labels create drastically misaligned
I'll
expectations.
light it now.
Two analysts can look at the exact same code, but their personal experiences, their stress levels, and their risk appetites are going to result in completely different dread scores.
So the math formula is basically just a formalized vibe check.
Yes. And that subjectivity creates a massive operational bottleneck that the industry calls analysis paralysis.
I can vividly picture a conference room full of tired engineers just endlessly arguing over whether a bug is a 6 or an 8.
That is exactly the reality of subjective frameworks. Engineering teams, by their nature, despise ambiguity. When there's no objective truth to anchor the score, threat triage just degrades into this prolonged philosophical debate.
Which helps no one.
Exactly. The sources explicitly warn about this friction. Instead of writing code and actually patching the vulnerability, the entire engineering team wastes an hour arguing about the definitions of high versus critical. The framework designed to speed up prioritization ends up bringing the workflow to a grinding halt.
Which completely defeats the purpose for our junior engineer. If dread causes conference room brawls, how do we escape this analysis paralysis?
Well, the industry moved to what the sources call the decomposition solution.
Decomposition solution.
Right. The goal is to strip the human feeling out of the measurement entirely. To do that, we have to break down abstract concepts like probability and impact into highly granular, measurable binary attributes that literally any engineer will evaluate exactly the same way.
You know, this reminds me of how car insurance companies calculate risk.
How so?
They don't just look at a driver and subjectively guess, like, looks like a risky teenager, let's charge them a lot.
Right.
They decompose the risk. They measure the exact age of the driver, the horsepower of the vehicle, the daily commute distance in miles, the historical accident rate of that specific car model. They plug those hard facts into a formula to calculate a premium.
That is a fantastic parallel. You move from subjective feeling to objective fact. In cybersecurity, this methodology gave rise to CVSS, or the Common Vulnerability Scoring System.
CVSS.
Yes, it evaluates known IT vulnerabilities on a severity scale from 0 to 10, but it avoids the subjectivity trap of dread by using 3 highly structured metric groups: the base group, the temporal group, and the environmental group.
Okay, let's decompose those groups. What falls under the base metrics?
The base metrics represent the intrinsic, unchangeable facts about a vulnerability. This includes the access vector, like does the attacker need physical access to the machine, or can they launch the attack over the internet?
Okay, binary.
Exactly. It also looks at authentication. Does the exploit require a valid password, or can an anonymous user trigger it? And finally, it measures the impact on the CIA triad.
Well, let's define the CIA triad really quickly for our student listener.
Okay.
That stands for confidentiality, integrity, and availability.
Yes, exactly.
So the CVSS formula is objectively asking, was data stolen? That's confidentiality. Was data maliciously altered? That's integrity. Or did the system crash and go offline? That's availability.
Yes. Those are purely factual questions with binary answers. A vulnerability either requires a password or it doesn't. It either alters data or it doesn't. There's zero room for a senior and junior developer to argue over a vibe.
Right?
Once you have those facts, you look at the temporal metrics.
Temporal meaning time. So these are factors that change as the situation evolves.
Exactly. The most crucial temporal metric is exploit code maturity. When a vulnerability is first discovered, it might only be a theoretical concept discussed in a research paper somewhere.
So the temporal score starts low.
Right. But weeks later, if a hacker publishes a fully automated attack script on the dark web, the temporal score spikes because the real-world danger just multiplied.
Well, that makes sense. That leaves the environmental metrics.
So environmental metrics allow an organization to tailor the objective score to their specific network architecture. A nasty vulnerability sitting on a public-facing e-commerce web server is going to have a massive environmental score.
Obviously.
But that exact same vulnerability existing on a testing laptop that is completely disconnected from the internet, that will have a very low environmental score.
So our junior engineer takes the facts, plugs them into the CVSS calculator, gets an objective score, and everyone in the conference room agrees. It sounds like the subjectivity problem is totally solved.
Well, it solves the subjectivity problem, yes, But it introduces a fascinating new challenge. A major criticism of CVSS highlighted in the source material is that the underlying math heavily inflates the scores.
Wait, how so? If the inputs are objective facts, how does the math get it wrong?
Because the CVSS base formula measures the theoretical maximum impact in complete isolation. It assumes the attack is 100% successful, and then it multiplies the worst-case scenarios of confidentiality, integrity, and availability together.
Okay.
What it entirely fails to calculate is the actual probability or likelihood of an attacker attempting the exploit in the real world.
Oh, I see. So it evaluates the explosive power of the bomb, but doesn't factor in whether the bomb is actually armed or if it's just sitting inside a locked vault.
Yes, exactly. Because it ignores probability and focuses on the absolute worst-case scenario, the distribution of CVSS scores is incredibly skewed. The research data shows that a massive percentage of vulnerabilities receive scores of 7.0 or higher.
Which brings our junior engineer right back to square one. If the math artificially inflates everything to a 7, an 8, or a 9, then the dashboard is still a giant wall of red. If every single alert is labeled a critical priority, then nothing is actually a priority.
You escape analysis paralysis but walk straight into alert fatigue. This is a very real friction point in the industry right now. Teams are just drowning in high-priority CVSS scores for vulnerabilities that will realistically never be exploited.
And there's another layer of complexity for developers, right? CVSS is designed to score known vulnerabilities, what the industry calls CVEs, or common vulnerabilities and exposures.
Right, the publicized ones.
Yeah, these are flaws that have been publicly identified and cataloged, but developers are constantly running automated code assessment tools that scan their work in real time, and those tools spit out thousands of raw, unfixed code weaknesses long before they ever become a public threat.
Ah, yes. You are talking about CWEs, or common weakness enumerations.
Right.
A weakness is simply a mistake in the architecture or the code itself. For example, failing to properly validate the length of text a user types into a login box. Under the right conditions, sure, a hacker can weaponize that weakness into a buffer overflow vulnerability, but in its raw state, it is just a coding error.
And CVSS can't score thousands of raw coding errors that haven't been weaponized yet. The math just wouldn't work.
Which is exactly why the industry introduced CWSS, the Common Weakness Scoring System.
CWS got it.
It was co-sponsored by the Department of Homeland Security specifically to provide a quantitative measurement for underlying software errors. And notably, it operates on a much wider scale of 0 to 100 rather than 0 to 10.
Well, a wider scale provides much more granularity to prevent everything from clustering at a 7, like with CVSS. How does the CWSS formula calculate that 0 to 100 score?
The overarching formula dictates that the quantitative score equals the impact score plus the exploitability score. To achieve this, it multiplies 3 distinct subscores. First is the base finding, which evaluates the inherent technical risk of the coding mistake. Second is the attack surface, which measures the barriers an attacker must overcome to actually reach that vulnerable code.
And the third subscore.
The environmental subscore. But how CWSS handles environment is truly innovative compared to the older models. It introduces a concept called vignettes.
A vignette, like a short story or a specific scene.
Sort of, yeah. The framework recognizes that business context dictates risk. A buffer overflow weakness in a hospital's patient database carries a vastly different real-world impact than the exact same buffer overflow in, say, a smartphone game.
Oh, absolutely, because one violates healthcare compliance laws and literally risks human life, while the other just crashes a game of solitaire.
Right. So CWSS utilizes over 23 distinct business domain vignettes. There are specialized scoring frameworks for banking and finance, public health, national defense, emergency services.
Wow. That is incredibly practical. It allows a developer to apply real business logic to raw code errors.
Exactly.
Like a healthcare developer can prioritize the weaknesses that threaten hyper-compliance, while a banking developer can prioritize weaknesses that threaten financial transactions, all without relying on their subjective personal feelings.
It bridges the gap between raw code mechanics and high-level business risk, mathematically.
So let's zoom out and look at the journey we've just charted for our junior engineers staring at their mountain of alerts. We started with the foundational Microsoft DREAD model. It taught us to look at threats through 5 lenses: damage, reproducibility, exploitability, affected users, and discoverability.
But we saw how the qualitative nature of DREAD leads to subjectivity. And that subjectivity sparks endless debates in conference rooms, leading to analysis paralysis where nothing actually gets fixed.
To solve that, we explored the decomposition solution. We move to objective binary facts using CVSS to evaluate known vulnerabilities based on base, temporal, and environmental metrics. And for raw code errors, we looked at CWSS using its 0 to 100 scale and industry-specific vignettes to prioritize mistakes before they can even be weaponized.
Mastering the philosophy behind these scoring systems is truly the key to cutting through the noise. It's how you look at a dashboard of hundreds of flashing red icons and confidently map out a mitigation strategy based on math and business context, rather than panic.
It gives you the power to actually shrink the mountain. But, looking at the evolution from subjective dread to objective CVSS, it leaves me with a final thought to ponder. We saw how the CVSS was built to completely remove human intuition, right? But because the math multiplies worst-case scenarios without calculating probability, it artificially inflates scores and causes alert fatigue.
Yeah, the pendulum swung almost too far toward widget math.
Exactly. So here is something for you to think about as you prioritize your next security sprint. If mathematical frameworks currently struggle to weigh the real-world probability of an attack, will the future of threat ranking have to circle back and reintroduce human intuition? Or will artificial intelligence step in to replace these manual scoring models entirely, constantly simulating millions of attacks in real time to show us exactly what will break first? The mountain of bugs is never going away, but the tools we use to climb it are about to change drastically.